video, we are going to see the 4 types of responses, step responses for a second order transfer function. Okay, when a second order transfer function, a system with a second order transfer function is given a step input, we can get different type of responses based on the value of the zeta, the damping ratio. If zeta is 0, the response is called undamped. Okay, it is oscillating forever, it never damps, as shown here. When zeta is from 0 to 1, then the response is underdamped. Underdamped means it oscillates, but oscillation damps and then slowly it saturates to a specific value. Okay, then when the zeta is exactly 1, we get critically damped, where it increases and it doesn't oscillate, it immediately saturates to a specific value. And then if the zeta value is bigger than 1, we get overdamp. Overdamp is similar to this critically damped, but it increases a bit more slower. It's much more damped. So it increases slower and it saturates after slightly longer time. We can look at this plot. It compares all the 4 type of responses. When zeta is 0, it's undamped. It's oscillating forever. When zeta is 0 to 1, it oscillates but slowly saturates to a specific value. When zeta is equals to 1, exactly 1, it doesn't oscillate, it increases and immediately saturates. When zeta is greater than 1, it increases much more slower. It's much damped a lot more. So increases slower and saturates at a longer time. Okay, so these are the 4 types of responses. Now we have seen the step response plot. It's also important to note the pole locations. Okay, if you find the pole of this transfer function, for undamped, both poles are located at the imaginary axis. For underdamped, both poles are complex numbers. Okay, for critically damped, these 2 poles will actually come and merge to one specific real value, a negative value here. So both poles have the same value. Okay, and then for overdamped, both poles will be 2 different negative real numbers. So these are the positions of the poles. Okay, I also want to share this. Let's see. Here is the value of zeta. When zeta is 0, we get undamped response. Okay, this is undamped, where there's no damping. Now when I increase the value of zeta, you can see it's slowly becoming underdamped. It's oscillating, but it's also saturating eventually. Okay, as you can see here, there's oscillation, but eventually it saturates. So this is called underdamped, and it happens until the value of this becomes 1. Okay, this is critically damped. When the saturation, the oscillation is completely gone, it increases and immediately saturates. This is critically damped when your zeta is 1. When zeta is more than 1, it's overdamped. Okay, it increases, saturates, but increases slower, and then it saturates. Let's look at the poles position. Okay, when zeta is 0, undamped, we have 2 poles at the imaginary axis. When zeta is between 0 to 1, this is underdamped. We can see both the poles are complex numbers. Okay, they are complex numbers. They are not at this axis, but they are inside the plane. Okay, as we increases, they come, and then at one point, when zeta is exactly 1, both poles merge at a specific real number. Okay, this is critically damped. And when we increase even further, they split into the 2 different real numbers. This is overdamped. Okay, so that's all. Thank you.